Hello. We are now in the last section of this chapter. So if you're getting tired of this material, that's okay because it won't take too long. And as with most chapters in this book or in math books, it ends with a section on applications. So you take all the things you've learned so far in this chapter and use them to do, to help you with real life situations. And we all know by now that applications, it's kind of code word for word problems. So all these problems, they're going to be kind of similar to what we've seen before, where you read the problem carefully, draw a picture if there's a shape, I guess, like a circle or a rectangle or a triangle, that kind of thing. Draw a picture, label it. If there's nothing to draw, then just see if you can set up an equation kind of slowly by reading the words they give you a couple at a time. But once you set up the equation, kind of the only thing new in this application section as opposed to other application sections is that the type of problem that you're going to set up, it's going to look more like an equation that's quadratic in form, like we've seen. I think we talked about this in the previous section or the section before. I think this is the previous section, the section before this, we said this is called a quadratic equation. So we can kind of expect, once we set up these word problems as equations, we can tell that they're probably going to look something like this, and then we're going to factor it to solve, like we learned in the last section. So this section will be very similar to the last one. It's just we have to set up our own equations based on the words they give us. But we've been practicing that for quite a few application sections at the end of a bunch of chapters. So I think it'll be good as long as the previous section made sense where we were factoring to solve equations. All right, and there's not a lot of things to talk about before to prepare us. It's just more set the problem up, factor it. Set the problem up. But like in the last section, you want to make sure that you have all the terms on one side, because remember, if you're using this property of zero products, you better have a zero on the other side of your equation before you try to factor. So try to keep that in mind. But let's just try one. I mean, there's not really a lot of theory behind it. There's not a lot to talk about before just trying a problem. Example 1 here. Okay, it says, a number is 30 less than its square. And thinking of square as not the shape, but square as the number to the second power. Find all such numbers. I guess like with all application sections, I'm probably going to let my variable be what I'm looking for. So what are they asking me to find? All such numbers. So I guess they're talking about some number that has this property that it's 30 less than its square and all that type of stuff. So I'm going to say x is the number we're looking for. Or I guess numbers plural, because the question asked, or they want us to find all such numbers plural. So I guess just x is the number that has the property they mentioned. Okay. And then now I'm going to read it little by little. Let me see. From the first couple words they say, a number. And then right off the bat I can say, well, I called that number x. So my equation is going to start with x. I know that for sure. I'm setting up my equation. Let me read another word. Is. Remember, is code word for equals. So I know that's coming next. A number is means x equals. And then how about 30 less than? I'm not even going to worry about what is less than. 30 less than means you're subtracting 30 from something. I don't know what yet, but we'll see. 30 less than what? The next couple of words are its square. And in that, they're talking about the square of your number, so x squared. Its square, yeah, you're talking about the number, so it must, when they say its square, they must mean that guy's square, that x squared. So I think that's our equation there. A number, x, is equals 30 less than, okay, that means you're subtracting 30 from something, its square, which is the square of the number you're looking for. All right, I think this looks good. Let's see now. Now I want to solve this, but like we said, in order to solve this, you're going to have to factor. But before you factor, you have to make sure you have all your terms on one side. And this is actually a really good example of something I wanted to point out. Here we have a choice of which side to bring all the terms on. We can move the two terms that are on the right side to the left side, or we can move the term that's on the left side to the right side. There's going to be an easier way to do it. One way is easier than the other. And to determine which side to bring all the terms on, let me see, you want to bring... This goes for all equations of this type where you're trying to factor to solve. Bring all terms to whichever side, I should say that leaves, sorry, using correct grammar here. To whichever side that leaves the leading term. And if you remember, we said before that leading term, that means the term with the highest power. So I'm looking at x squared here. He's got the highest exponent. So you want to bring all the terms to whichever side that leaves the leading term positive. So right now, where x squared is, he's already positive because his coefficient is a 1, a positive 1. But imagine if I try to move him over to the left side, I subtract him. Notice now he'll be a negative x squared. And that's what I don't want, because it's harder to factor when your leading term is negative. So I think that would make me want to move everything to the right side. Since that way x squared wouldn't have to move and he wouldn't have to become negative. And it's actually easier to move everything to the right side, because all I have to do is subtract the x that was on the left. Now it's on the right. That's not too big a deal. And now there's nothing on the left side, which is good. Like we said, when you try to use the property of zero products, you want 0 on the left or the right side. It doesn't really matter, as long as all the terms are on one side, and then 0 is left on the other side. And I want to write these terms in descending order of power, so I'll write x squared and then minus x, and then the constant minus 30. And now that I have all the terms on one side, and they're in descending order of powers, I'm going to factor this guy. And since this is a trinomial, it has 3 terms, and there's no number in front of x squared, it's just a coefficient of 1. That means this will be the easy factoring method, where I just have an x, and then I'm looking for what 2 numbers multiply to negative 30 but add up to negative 1 here. Let's see, I think of negative 6 and positive 5. Negative 6 times 5 is negative 30, which is good, and negative 6 plus 5 is negative 1. So I think we found the numbers. Now it's time to set each of these factors equal to 0 and find our 2 solutions. So this factor on the left is equal to 0, we'll solve that. The factor on the right is equal to 0, and we'll solve that. And those will be our 2 solutions to this this application problem. To solve the one on the left, I'll add 6 to both sides. And that'll leave me with x equals 6, or 6 equals x, same thing. So 6 must be one solution. The other one, if I solve the one on the right, I'm going to subtract 5 from both sides. And that'll leave me with negative 5 equals x, or x equals negative 5, however you want to think of it. There he is, alright. So those are our 2 solutions. Those are the numbers that are 30 less than their squares. That's kind of a complicated statement, but as long as we translate it into an equation, it should be fine, and we'll solve it, and it's perfectly fine. I guess if you want to check, you can make sure, like let's say we want to check 6. That was the first solution we found. We want to make sure, like they said, that the number is 30 less than its square, if I square 6. And that is true, because 6 squared is 36. 36 minus 30 is 6, so that works. I guess that's how I'd check it. It's kind of like you just have to plug it into your original equation you set up. But yeah, then you could try negative 5, and that should work as well. Alright, might as well try example 2 now. I think we're on a roll. So example 2 here says, the product of 2 consecutive odd integers is 195. Find the integers. Alright, well the first thing we're supposed to do is set a variable for the thing you're looking for. This one, it's kind of tricky because we're looking for 2 things. Because they said that there's 2 consecutive odd integers that we're looking for. Maybe I'll say x is the first consecutive odd integer. Odd integer, okay. I gotta think about the second one. I don't know what I'm gonna call that one yet. Second consecutive odd integer. So let's say if I call this guy y, then the equation I set up, it'll have x and y in it, but I'm not able to solve an equation that has 2 variables. I can only solve an equation that has 1 variable, like the one we found in example 1. So I think we're not going to be able to call the other one y. We're going to have to think of, how can I write the second variable in terms of the same variable x? Is there some relationship between the 2 numbers that allows me to say, okay, well if the first one's x, the second one is something involving x? Well, if you think about, okay, what do they mean by consecutive odd integers? Let's see, consecutive, it kind of helps me to think of an example, like let's see, what are consecutive odd integers? There's any 2 pairs of numbers that are odd that are close to each other, like 11 and 13, for example. Those guys are consecutive odd integers. They're, one's odd, the next one is the next odd number that would come if you count, 11, 12, 13. So I noticed, though, that when I think of an example like this guy, I don't know if this is the right answer. I don't know if these are the numbers I'm looking for. I'm just trying to kind of brainstorm to see consecutive odd integers, what kind of relationship do they have with each other? You notice that they're 2 apart. If I take 11 and I add 2, I'm going to get 13. And any other odd integers you come across, they'll be the same way. They'll be 2 apart. Like if you took, I don't know, 101 and 103. Those are consecutive odd integers as well. And if you take the first one and you add 2, you're going to get the next one. So I think that's going to give us our relationship. If the first one's x, the second one's x plus 2. Because it's 2 further along in your counting numbers than the first one was. Okay, that'll give us a way to write the 2 things we're looking for, but in terms of the same variable. Because like we said, if you don't get them in the terms of the same variable, you'll have an equation with 2 variables. It'll be impossible to solve. So that's what you want to make sure of that. Get both in terms of the same variable, not different ones, because that'd be a waste of time. You can't solve it. It would seem like it would be a lot easier to get them in terms of different variables, just call one x and one y, but it wouldn't be helpful because we couldn't solve the equation. Alright, now that I have an expression for each one, x and x plus 2, let's read the problem and see if we can set up an equation. The first thing they say is the product of something. Remember, the product of something, or a couple things, means you're multiplying. That'll be something times something, and then let me see what do they mean. The product of what? 2 consecutive odd integers. Well, those are the things we just labeled, right? X was the first one, x plus 2 was the second one. So that must be the product of the things we want. The first guy times the second guy. The product of those guys, and then what? Is 195. So remember, is code word for equals. And then after equals, I guess 195, I don't know what else to do with that. There it is. So the product of the first and the second is equal to 195. And this is now something we can solve. X times x plus 2 is 195. And I think this one is similar, or this equation is similar to the very last example we saw in the previous section. Remember we said, oh, right now it looks like they've kind of factored it for us, and it seems like, wow, they're really being nice. That was nice of them to factor it. But remember, it's only useful if you have all the terms on one side, but 195, he needs to move over to the other side so that you have 0 on the right side, say, and then we'll have to refactor it. So really we're going to have to multiply this out and then factor it again once we move the 195 over. And then I think the first thing I'll do, I put parentheses around this x, but I don't think they really need to be there. They may be kind of confusing me, actually. I think I'm going to take them away. And then I'm going to multiply the left side out. Let me distribute this x here. Now that I realize that it being in factored form is not really helpful because the 195 was not involved in the factoring. So if I multiply that x in, it'll be x squared plus 2x. And now the 195 is on the right side. Now I have to move the 195 over by subtracting it. And then I'll factor whatever I get when I move it over. And of course, in descending order of powers, x squared plus 2x, and then the constant minus 195. Let's see here. Now I'm going to try to factor that guy. Now this one, thankfully, it's a similar type of factoring to the last problem because I have a trinomial, 1, 2, 3 terms, and the leading coefficient is a 1. So I'm able to factor it pretty simply. It's going to be x plus something, or x minus something, and another x plus something, or minus something. I'm not sure. Kind of depends. But the numbers I would be looking for, they must have a product of negative 195 and a sum of 2. And I'm not really familiar enough with 195 to think about that, so I might have to think like 195, what can go into 195? Well, I know 195 can be 1 times itself, but there's no way, no matter which of those numbers, 1 and 195, no matter which of those I make negative or positive, there's no way they're going to add up to 2. That's not going to happen. Does 2 go into 195? No. Does 3 go into 195? I think so. 3 times what? Let's see. See, it's 3 times 65. But I think those are too far apart still. There's no way, no matter which of those I make negative and which I make positive, there's no way those are going to add up to 2. So let's try another one. I think 4 doesn't go in. 5 goes in. How many times? Okay, 39 times. Those are still too far apart. No matter which of those you make negative or positive, you're not going to get 2 when you add them together. So I got to keep thinking. What else is there? What does 6 go in? No. 7 go in? No. Does 8? No. 9? No. 10? No. 11? No. 12? No. 13 does. Okay, whew. 13 times, let's see, 13 times 15 actually. Huh, who would have thunk it? So yeah, if you're ever stuck and you say, man, I really don't know what multiplies to make this thing, just start trying to divide it by 1, 2, 3, 4, 5, on and on and on. And eventually, once you divide it, you'll find a pair that actually adds up to what you want. Because I think 15 and 13, those are 2 apart. So I can say, I guess if I want them to add up to a positive 2, I'd have to make the smaller one negative, right? So the 13 negative and the 15 positive, those will be my numbers. Let me kind of rewrite this a little larger. I can't really see it. So it'll be x minus 13, x plus 15. Or the other way around, if you wrote x plus 15 and then x minus 13. Doesn't matter, as long as the correct sign is with the correct number. Alright, now that we factored it, the very last step would be to set each of those factors equal to 0 and solve for x. So I'll have x minus 13 equals 0. X plus 15 equals 0. And those are my numbers. So let's see, I'll add 13 over to this side. And that'll give me x equals 13. Let me subtract 15 on both sides here, and that'll give me x equals negative 15. So notice, if you look at these guys, 13 and negative 15, they're not consecutive odd, or they're not consecutive odd numbers. These are far apart. Like, if it was positive 13, positive 15, then those would be consecutive odd numbers. But the fact that one of them's positive and one of them's negative, they're not the pair of numbers I want. But if I remember, if I just found x, remember what x was? X was the first number. So that means we have 2 options. That the first number, it could have been 13, and I don't really know what the second number is. Or it could be that the first number was negative 15, and I don't know what the second number is yet. So I actually am not done yet. I have to find the second number, because they want to know what both of them are. And remember that the second number, we found an expression for the second number. The second number, in either case, we wrote it up here as x plus 2. So if I take either of these x values, and I substitute them into x plus 2, I'll be able to figure out what the other one is. So okay, the first one I got was x equals 13. That would mean x plus 2 is 13 plus 2, or 15. Okay, so there's one pair of numbers. If x is 13, that's the first number, and the second number is 15. That's one possibility. The other possibility is that the first number was negative 15, and the second number is x plus 2, and x was negative 15, but I'm adding 2 to that because that's the next consecutive number. Negative 15 and 2 is negative 13. Now, so there's another possibility. It could have been, so we have 2 options. They were saying, hey, find these 2 consecutive odd numbers that have this property, and we found that there are actually 2 pairs of consecutive odd numbers that have the property they want. It could either be 13 and 15, which that's probably the more obvious one, I guess, because they're both positive. But also, technically, technically it could have been negative 15 and negative 13, because those are consecutive odd numbers. And their product is what? What did they say? Their product is 195. That's true, because it's a negative times a negative, so it's going to make a positive. So yeah, you have to actually have 2 pairs of answers there. That's kind of tricky. Alright, that was a lot of work right there, huh? Let's try another one here. Example 3. This one sounds kind of interesting. What does it say? The work surface of Anita's desk is a rectangle that is 5 feet... Oops. Shoot. Sorry. It's 5 feet longer than it is wide. Find the length and width if the area is 84 feet squared, or square feet. Alright, this is one... I mean, it's up to you. If you feel like you can set this up without drawing a picture, that's fine. But I just think... I always have to draw a picture and label the sides. I think that always helps, if it's kind of a geometric figure. They're saying the work surface of Anita's desk is a rectangle. Okay, I've drawn a rectangle. It's 15 feet longer than it is wide. Well, I don't know. It kind of doesn't matter which side you put as the length and the width. But this side looks longer, so I guess if I say this length is x, then this length, they said 5 feet longer, then it would be x plus 5. And I think that works, because what they're asking for is the length and the width, and I've labeled a variable to be one of those, and x plus 5 to be the other. So I think that works. Hopefully that makes sense, yeah, because they said if whatever one length is, if you call it x, and the other length is 5 feet longer than that length. So since I called the first one x, the second length will be that plus 5. Alright, so we've got an expression for both. Let's see if we can set it up in an equation. Is there anything in this problem that we haven't used yet? The work surface of her desk is a rectangle. Okay, we've drawn a picture of that. It's 5 feet longer than it is wide. Okay, we've already used that to come up with the x and the x plus 5. There must be something else we can use. Find the length and the width. Okay. If the area is 84 square feet. Okay, there it is. So if you remember, the area of a rectangle, it's length times width or base times height. You know, it doesn't really matter how you call it, just the two dimensions multiplied together. Since we know the area is 84, that means the length times the width is 84. And we know an expression for both of those things, the length and the width. It doesn't really matter which one's which. Let me say x is the length and x plus 5 is the width. If you did it the other way around, x plus 5 is the length and x is the width, it wouldn't matter. You're going to get the same answer either way. But yeah, now I can replace L, the length, with x, because we know that's the length of this thing, and then the width with x plus 5. And now we have an equation we can solve since there's only one variable left, and everything else is just numbers. So this one actually looks kind of similar to the last problem because it looks like one side's factored for us, but that wasn't really helpful because we don't have all the terms on one side. What we have to do like we did in the last one is undo the factoring by distributing this x. It'll become x squared plus 5x. And then once we do that, we'll have to move all the terms to one side and try to factor it. But to determine which side to bring all the terms on, I'm going to see, okay, which one's the leading term? X squared is the leading term because he's got the highest power. I want to make sure he's not negative. So I want to look around and say, all right, which side would I have to bring everything on to make sure that that guy stays positive? Well, he's positive where he is right now, so I do not want to move him. I'm going to move the 84 instead, so that way everything's on one side and my leading term is still positive. Alright, let's see, if I move the 84 over, he becomes negative, and then I'll have 0 equals x squared plus 5x minus 84. And I want to try to factor this. This is another one we're getting really lucky here. This is one of those easy trinomial factoring methods because there's a 1 in front of the x squared, the coefficient. We don't have to use that x method, thank God. But now at this point I'm looking for the numbers that multiply to 84, or negative 84, and add up to 5. So I'm not really familiar with 84 that much. I'm going to think about 84. He could be 1 times 84, but those are too far apart. No matter which of those I make negative or positive, I'm not going to add up to 5 like I want. Let's see, what else goes into 84? 2 times 42. Those are also too far apart. There's no way you're going to add up to 5 if you make either of those negative or positive. Let's see, does 3 go into 84? I think so. 3 times 28. Oops. Those are still too far apart. Okay, what about 84 divided by 4? That'd be 21. Those are still too far apart. Does 5 go into 84? No. Does 6? Yes. 6 times 14, I believe. We're getting closer because those are closer together, but they're still a little bit too far apart. Let's try. Does 7 go in? Yes, 7 goes in 12 times. Ooh, and look at that. Those are 5 apart, I think, right? 7 plus 5 is 12. Okay, but let's see. We want these numbers to multiply to a negative, so I know either 7 or 12 is going to be negative, and the other one's positive. But we want them to add up to a positive 5. So it must be that the smaller one is negative, so the 7 is negative. Alright, that must mean I want a negative 7 and a positive 12. So those guys would have a product of negative 84 and a sum of positive 5. Alright, now that we've factored it, we can set each factor equal to 0. The left one, x minus 7 equals 0, and the x plus 12 equals 0. And once we solve either one, that's going to be a winner. Let's see, I'll move the 7 over to solve this guy. We've got x equals 7, good stuff. Or 7 equals x, either way. And the other one, if I want to solve that guy, I'm going to move 12 over. Once I subtract it, I'll find that x is negative 12. Alright, but we're not done because, remember what they asked for was what are the dimensions, which means what are the length and the width. And remember that x was just one dimension. It was either the length or the width. So we found two options for, I don't know, let's just say x is the length. It doesn't really matter which one's which. So we found two options. The length of this table could either be 7 feet or negative 12 feet. You know what, just saying that out loud makes me realize negative 12 is not a winner. Since this represents something in real life, whereas the last example just said, find 2 consecutive odd numbers. Those could be negative or positive because they're just numbers. But this is in a real life example where we're talking about the length of a rectangle or the length of a table. No such thing as negative length. So this guy's out. That can't be the right answer. But think about that on some of these problems. If something represents something in real life, and that value cannot be negative, like the length of a table, or I don't know, there's all kinds of things in real life that there's no way they can be negative. It doesn't make sense. No such thing as negative length for a table. There's no way. Like, what if someone told you, oh yeah, the table I have at home, it's negative 12 feet long. Isn't that crazy? You would think they're crazy. It's like, sure. Crazy person? You don't want to mess with them because they're a little bit off. So it must be the 7 feet is the length. Alright, that must be the winner, but they did say they want both the dimensions. So I do know the length is 7 feet, but I don't know the width. Remember they said the other dimension, or we labeled it on the, on the picture. It was x plus 5? Is that what it was? Yeah, x plus 5. Remember this guy here. That must be the other dimension, x plus 5. And since we know x, it's 7. It's 7 plus 5. So 7 plus 5, that's 12 feet. Okay. And I guess I should be saying these in words, huh? Like a sentence. So if I want to sum this one up, I should say the length of the rectangle, or no, I'm going to say the table, just to keep it simple, has dimensions 7 feet by 12 feet. Because those are the dimensions that we just found just now. Alright, that was a good problem. I think it really helped to draw that picture. I don't know if I would have come up with, the length of one is x and the other one's x plus 5. That's kind of tough unless you label it. Yeah, and if you ever get stuck, don't panic on a problem. Just kind of picture things and see what you can do. Look at the problem and see if there's any information you haven't used yet. Like in that last one, 84 square feet was at the very end. And I knew I hadn't used that yet. That was kind of the key to setting up the equation there. Alright, let's try this next one. What do we have? It says the height of a triangular mainsail on a sailboat is 5 feet greater than the length of its foot. I guess they put a quote-unquote there because foot must be like the base length of the triangle. I don't know, maybe that's a sailing reference or something. If the area of the sail is 42 square feet, find the length of the foot and the height of the sail. So they don't say it here, but I think what they're saying is that this is a right triangle. So I guess imagine this is your sail. I mean, it's like one of those old sailboats that look like, there's one sail there, there's probably another one here I'm not worried about. And it's being, there's some cute little boat here. Look at that. Is this art class or is this math? Terrible drawing. But anyway, I think they're just thinking of a sail as a right triangle, not a big triangle, just the right one. And in the review section, if you remember, we talked about right triangles. And we said, remember the Pythagorean theorem. It said that the lengths of all the sides have this property where you take the two shorter sides and you square them, a squared plus b squared. It should be equal to the square of the longest side. So this guy's the longest side, of course. It's the side across from the right angle. And the other sides don't really matter. I'll call maybe the foot or the base of it A, and then the height of it B. Although it doesn't matter. Alright, but now that I'm looking at this problem, the height of the rectangular sail, I don't know if the Pythagorean theorem is going to help us, huh? I think I jumped the gun on that one. Sorry, guys. I was thinking, the Pythagorean theorem. But, let's see, I don't think they even reference, they only tell us they only reference the length and the base. I'm sorry, the height and the base. So they give us something about this length, and they give us something about this length, but they don't mention the hypotenuse or the longest side at all. So I think actually the Pythagorean theorem won't be helpful here. Sorry. I don't know if you guys ever do that. Jump the gun and just assume this is the way I'm going to solve it, and then it doesn't work. Sorry. So what does it say? Okay, the height of the triangular mainsail is 5 feet greater than its length. So I guess if I call the length x, then the height is 5 feet greater. So kind of like in the last picture we drew, one of the dimensions is x, and one of the dimensions is x plus 5. Alright, sounds good. We've labeled everything, and the two things they're looking for are the base and the height, which we've labeled, and they're both written in terms of one variable, which will be good. Now we just have to think of an equation, and I think similar to the last one, there's one piece of information we haven't used yet, the fact that the area of the sail is 42 square feet. So it'll be similar to the last one, it's just, now we're not talking about a rectangle. A rectangle has area, length times width. A triangle, though, has a slightly different formula. The area is 1/2 base times height. So it's similar. It's the base times the height, like the area kind of, except you have to have the 1/2 in there. So looking at that, the area formula for a triangle, I'm going to try to fill in everything I know. Well, the A for area, I know that's 42. They told me the area is 42. So I can go ahead and replace that. Equals 1/2. See if I can replace the base and the height there with some expression for a variable. But thankfully we wrote those out. The base we said was x here. So I'll replace that guy. And then the height was x plus 5 here. There we go. Alright, I think even though this equation looks complicated to solve, at least it's something we can solve because it's just a bunch of numbers and one variable. Even though that variable occurs twice, that's okay. We're still able to solve it. If I want to solve this for x, you know what I think I'll do? If you remember, if you have an equation and it has a fraction or even more than one fraction, if you don't like that fraction in there, you can always get rid of it by multiplying both sides by the least common denominator. So if you want at this point, you can multiply both sides by the LCD, which since there's only one fraction, that denominator is the LCD. The LCD would just be 2, because that's the only denominator. I'm going to go on both sides and multiply both sides by 2. And that should knock out that fraction. It'll make the left side larger, but at least it'll make the right side simpler. So keep that in mind, if you ever have an equation with a fraction in it, or more than one fraction, you're free to look for the least common denominator, multiply both sides by it, and that should simplify it quite a bit. But it might cause some numbers to be a little larger, but I'd definitely make that sacrifice if I can get rid of my fractions. What will that do to the left side? 2 times 42 is 84. On the right side, I'm multiplying 2 times 1/2. If I put that 2 over 1, notice the 2's cancel outright. So this whole fraction times a fraction just becomes a 1. So it's really gone. 1 times x is just x. And then you have the x plus 5, just kind of carrying these variables over here. And now this looks a lot, actually, it is the exact same equation as the last one. What the heck? Oh my gosh, that was not on purpose. Sorry, you guys. Same equation as before. Oh my gosh. Well, just for practicing purposes, let's actually solve this pretending like we haven't solved it yet. Looking at this guy, I see that it's kind of factored, but it's not supposed to be factored since not all the terms are on one side. I better distribute that x there. 84 equals, it'll become x squared plus 5x. And now if I move the 84 over, subtract it, because I want to move everything to one side, and I want to make sure I don't move x squared since he's positive as he is. If I move him, he'll become negative. 0 equals x squared plus 5x minus 84 is what I'll end up with. And in this part, we saw that to factor this is the easy factoring technique with an x and an x. You'll be looking for the numbers that multiply to negative 84 and add up to 5. And we could do the same thing we did before where we come up with all these guys. What are all the guys that multiply out to 84? But eventually we got to negative 7 and 12. Those were the ones we wanted. And if you set each one of these equal to 0, x minus 7 equals 0, x plus 12 equals 0. What are we going to get here? I'm going to solve the first guy by adding 7. You get x equals 7, okay. If I solve the other one by subtracting 12, I get x equals negative 12. Like we said before, since this represents something in real life, this is the length or the base or the height of a sail. There's no such thing as a negative 12 feet long sail. That wouldn't make any sense. It must be the positive one. It's 7 feet. The base is 7 feet. That's how we labeled it, the horizontal distance. I just have to find the height now, but the height we labeled in the picture as x plus 5. All I have to do is replace x with 7 since we found x to be 7. X plus 5, 7 plus 5 is 12. Alright, there it is. So it must be 7 feet by 12 feet. Just like the last one. Sorry about that, I had no idea those would be the same exact equation when we set them up. The sail is, let's see, 7... I'm gonna say the sail has a 7-foot base. That sounds better. And a 12-foot height. I know there's all kinds of ways you could probably phrase that better, but as long as you kind of get the point across and write it as a sentence, that the sail, the base or the horizontal distance is 7 and the height is 12, then it should be fine. And that was funny. We got the same equation. Alright, so sorry if you're getting a little bit tired of this section. Application problems are kind of tricky. And this last two problems, they look complicated because there's some really weird equation they're giving us with a bunch of variables in it, like this guy, n equals x squared minus x. It looks scary, but I think these are actually easier because they give you the equation. Even though it looks complicated, they're giving me the equation and I don't have to go find it. Because that was the hard part of the previous 4 examples, was actually finding the equation based on the information they gave me. I think these will actually be easier. They've already given me the equation. Let's try example 5. It says, in a sports league of X teams, okay, it's good to kind of make a mental note that this equation they gave me, n equals x squared minus x, in that equation, x represents the number of teams, because they said in a sports league of X teams. So you can just keep that in your mind, or you can actually write it out to remind yourself. X is the number of teams, okay. In which all teams play each other twice, the total number n of games played. Okay, so that must be what n stands for. N is the number of games played. Okay, that's kind of tricky because x and n represent the number of something. You just got to keep track of which one's which. X is the number of teams and n is the number of games played. It's a little bit tricky, but either, yeah, keep that in your mind or write it down so you don't forget. If you have a terrible memory like me, you're going to want to write it down because I'll forget. Alright, what do they say now? The teams of a youth softball league play each other twice for a total of 132 games. How many teams are in the league? So I think it sounds like you're going to use this information here that they play each other twice. But that's not going to be used. It's really only there to tell you that you're able to use this equation. Because notice in the very beginning they said, oh, in a sports league of X teams in which all teams play each other twice, blah, blah, blah. This is the equation. So when they'd say down here they're playing each other twice, they're just letting you know, yes, this is a situation in which you can use this equation, because this equation is only used if each team plays each other twice. Alright, so don't worry about that. I think the key here will be a total of 132 games. So I just have to think about using the equation they gave me. They gave me n equals x squared minus x. What am I going to do with this number they gave me, 132, to figure this out? Well, I'd imagine I'm either replacing n with 132 or x with 132. And to tell which one I replace it with, or which variable I replace it into, I'm just going to remind myself, okay, 132, what did they say that was? It's the total number of games. So I just have to remember, was n or was x the number of games? Well, we wrote it here. Notice n is the number of games. X is the number of teams. They didn't give me that there were 132 teams. They said there were 132 games, and that's n. So it must be that I'm going to replace n with 132 and not x, because I guess I don't know what x is. That's actually what they're asking for, right? How many teams were in the league. It's kind of tricky, but to determine which variable you're replacing, make sure you know, well, what does that variable stand for? Is it games or teams? And then the number I'm given is that games or teams. You know, what are they telling me here? Alright, now I think we can solve this. So I notice we have an x squared and an x on one side, a 132 on the other. I need to move everything to one side. I'm going to move the 132 to the right because if I try to move the x squared and the x to the left side, the leading term x squared would become negative, and that's not good. That's going to be harder to factor. Alright, but if I move the 132 over, I think that'll work a lot better. And now that I have this, 0 equals x squared minus x minus 132, I'm going to factor that guy. And the good thing about this section is it's usually the easy factoring technique. This is another trinomial whose leading coefficient is a 1. Now all I need to figure out is what multiplies to negative 132 but adds up to negative 1. I think I'm going to have to think about that. What can 132 be? 132, well, I know 1 times itself is 132, but there's no way those are adding up to negative 1, no matter which of those I make negative and which I make positive. 2 can go into 132 66 times. Wow, that's a lot. Can 3 go into 132? Yes. 44 times, I believe. But there's no way any of these are adding up to negative 1, no matter which I make negative or positive. I have to keep going. Does 4 go in? Yes, 4 goes in 33 times. Those are still too far apart. I pretty much need 2 numbers that are only 1 apart in order for them to add up to negative 1. I gotta keep going. See, 4 goes in. Does 5 go in? No. 6 does go in 22 times. Those are getting closer, but they're still too far apart. I need them to only be 1 apart in order to add up to negative 1. So that's not going to work. Does 7 go in? No. Does 8 go in? No. 9? No. 10? No. I think 11 goes in 12 times. There it is. Those guys are 1 apart. Alright, so since I need them to add up to a negative, that means I need the larger of these guys to be negative. So it must be positive 11 and negative 12. There we go. So a plus 11 and a minus 12. Those must be the winners. Ugh, does that make sense? Yeah, those multiply. 11 times negative 12 is negative 132. And 11 plus negative 12 is negative 1. Okay, those are the right ones. Now let me set each of those factors equal to 0 to solve this guy. So x plus 11 equals 0, x minus 12 equals 0. Alright, let me see. If I solve the left one, I would have to solve it by subtracting 11 to the other side. And that'll leave me with negative 11 equals x. So think about that guy. How about the other one? If I want to solve for x, I'll add 12 to the other side. And I'll get x equals 12. But remember, this problem, it shouldn't have had 2 solutions. Because remember, if you remember, x stood for the number of teams here. So you wouldn't, if you ask, oh, how many teams are in this league? Someone wouldn't say, oh, negative 11 and 12. There's only one right answer. It's one or the other. I think this one's similar to the rectangle and the triangle. There's no way to have a negative number of teams. Yeah, no way. That doesn't make sense. So it must be the positive one. So it must be 12 teams. The softball league has 12 teams, or something like that, to indicate the subject that you're talking about and the answer that you got. Looking good. Alright, we got the last one here. This looks like a complicated equation, but I think if we take it one step at a time, it'll be doable. Alright, what is it talking about here? It says the height of a wave in a storm depends on the speed of the wind. Okay, that's kind of interesting already. Assuming the wind has no obstructions for a long distance, the maximum wave height, h, okay, keep that in mind. I guess I don't know if I need to write that down, h for height, that's not hard to remember. But oh well, just in case. Wave height, alright. The maximum wave height, h, for a wind speed of x. Alright, so now I know x is the wind speed. Okay, sounds good. That way I know in this equation what everything stands for. There's a h, there's an x. Now I know what they stand for. Okay, and keep in mind too that they're saying the units. H is in feet. Okay, so wave height in feet. I'll remind myself of that. And x is in knots, which are nautical miles per hour. Alright, it's good to know the units, because if they want the answer, they probably want the units in the answer as well. Alright, what are they asking here? For what wind speed would the maximum wave height be 3 feet? Alright, so really they're just giving me one number like in the last one. I just have to figure out, is this x or is this h? Well, they gave me that this is 3 feet is the wave height. So I just got to figure out, was the wave height h or x? That was h, right? So that means, okay, in the equation that they gave me, I'm going to replace h with 3. That's pretty much it, and then try to solve it. And the equation they gave me was h equals 0.03 y. X squared plus 0.6x. Come on. Minus 6. Blech. Alright, you gotta do what you gotta do. I'll replace, okay, they said 3 feet was the wave height. Put that in for h, because that's what h represents, the wave height. I'll put a 3 there and then try to think about how I'm going to solve this equation. It's not pretty, huh? But remember a couple problems back where we had, what did we have? We had a fraction and we said, you know, you don't have to put up with fractions. If you want to get rid of a fraction, you can multiply both sides by the least common denominator. You know, this is similar. To get rid of decimals, if you remember, you can multiply both sides by 10 or 100 or 1,000. Whatever you need, I guess, depending on how many times you need to move the decimal to the right. Well, since I notice the first number, 0.03 here, he has 2 digits beyond its decimal, so I need to multiply by at least 100, because that'll move the decimal to the very right of the 3. I think that'll work for the other guy too, right? If I move his decimal twice, he'll be a whole number. Alright, that'll work. I was going to multiply by 10, but if I multiply the first number by 10, that'll only make it a 0.3 instead of a 0.03. I'd rather it be a whole number. Alright, I'm going to go 100 on both sides. 100 times the left side, 100 times the right side. And it'll make some of the numbers bigger, but I think it's worth it. So 100 times the 3 that was on the left side, 100 times the entire equation that was on the right side, 0.03x squared plus 0.6x minus 6. Oops. There we go. Then of course on the right you're having to distribute this 100. 100 times the first term, 100 times the second term, and then 100 times the third term. On the left I think I can handle that. 100 times 3 is 300. On the right side, we already said that we kind of designed it so that this 100 moves the decimal to the right twice. That'll make that guy just a 3x squared. Yeah, because if you move the decimal on 0.03 to the right twice, it'll make it 3 point, or the decimal to the right of the 3, which means it's just a whole number 3. And if I multiply 100 times 0.6, so if you want to think about it up here, you could say, okay, it's 0.6. I'm moving the decimal twice, since it's multiplied by 100, and since I moved it twice, it's past the 6, and there's an empty space. If you remember, we have to put a 0 where there was an empty space. So it'll be a 6, and not only that, but a 0. And then the x. And then the last guy, 100 times -6 would be -600. Alright, even though the numbers are larger, I'd much rather deal with slightly larger numbers than decimals. But if you don't mind decimals, you could have left it as is and started solving it. It would have been really hard to factor, though. Alright, now that I look at this guy, it looks pretty good, but I notice I don't have all my terms on one side. I'm going to have to move this 300 over. I would move him over and not the other terms because I want to make sure that the highest powered term does not become negative. And where he is, he's positive. It's already good. But if he moved to the left side, he would become negative, and that's no good. So I move the 300 over. That's not going to affect the 3x squared or the 60x. But it will affect the last guy. -600 minus 300 is -900. Man, so these numbers are big, but remember when you factor, we haven't had to do this yet, but the first thing you're supposed to do is think, is there a greatest common factor? There is. All these terms have a 3 in common. So I got scared at first. I said, oh man, this is a trinomial with leading coefficient not 1. It was a 3. I was scared that I'd have to use the x method, but now that I factored the 3 out, I realized I don't actually have to do the x method, because now the leading coefficient of this polynomial is a 1. This will be the easy factoring method. Okay. So 0 equals, I'll keep the 3 outside. This is that easy factoring method. I just have to figure out what kind of numbers multiply to -300 but add up to 20. Ooh, that's kind of tricky. Let me see here. 300. That's a lot of options. He could be 1 times 300. There's no way that's going to add up to 20, no matter which of those I make negative and which I make positive. 2 times 150 makes 300, but those are still way too far apart. 3 goes into 300 100 times. Those are still way too far apart. There's 4 going, yes, 75 times. Those are still way too far apart. 5 goes in, let's see, how many times? 60 times, okay, 60 times. Those are still way too far apart. 6 goes in 50 times, still too far apart. This could be a while. Does 7 go into 300? No. Does 8 go in? No. 9? No. 10 goes in 30 times. Are those, those are the right distance apart. Those are 20 apart, right? And I want them to add up to 20. Alright, that means, if I want them to add up to a positive number, I want the smaller one to be negative. So 10 is negative, 30 is positive. Does that make sense? 30 times -10 is -300. Okay, good. 30 plus -10 is 20. Okay, good. We got them. Must be a -10 and a +30. Or the other way around. If you put +30 then -10, that's fine. Doesn't really matter. Whew. Alright. Well, set each factor equal to 0. Alright, let's see. Well, we've seen this before. This is kind of misleading. You see, it looks like 3 is its own factor, right? He's kind of in the front. But you notice if you set him equal to 0, that's not going to happen. You can't. There's nothing really to solve there. You can't solve for x. And you could just really use logic and say, alright, when would this happen? When is 0 equal to 3? Never. So that guy, he's not going to produce a solution. And I think we talked about that in the previous section. I think it was the previous section. If you ever have a constant in the front, and you're trying to solve an equation by factoring, that constant is not going to affect the answer. It's only the factors that have a variable that will actually affect the answer. So I'll solve the next one. That might actually give me an actual solution. I'll add the 10 to both sides, which will leave me with x equals 10. And I'll solve the last guy by moving the 30 over by subtracting it. And that'll give me x equals -30. Alright, so we got two options here. X equals 10 and x equals -30. I don't want to necessarily throw the negative away, because it might be you never know what situation you're in. Let me look. What were we talking about again? I already forgot. Oh yeah. What did x represent? X is knots, which is nautical miles per hour. It's like speed, right? So I think this one is true, though. We will have to throw the negative away, because there's no such thing as negative speed. Oops, sorry. Yeah, so I'll throw that guy away. No such thing as negative speed. Yeah, you wouldn't be driving down the freeway and say, oh, I'm going negative 60 miles an hour. People think you're kind of crazy. Alright, so it must be 10 knots. Okay. See, the value they gave us that the wave's height was 3 feet, and we found that the speed of the wave must be 10 knots. I'm going to try to sum that up. If a wave's height is 3 feet, that was what they gave us, the speed of the wave is what we found, 10 knots. Okay, there it is. That's our answer right there. Beautiful. Alright, this was a kind of a tricky section, but hopefully it made sense. Usually the last section in a chapter is always the hardest one, right? But we're going to start a new chapter next, and usually the first section is the best one. So it's kind of your reward for sticking with this whole tough chapter. We'll start a new section and should be good. Thanks.